All right, our next speaker goes by the synonym of gehackselt, which roughly translates to blended. Nevertheless, the true name, Sebastian Neef. Sebastian is a PhD student at the Technical University in Berlin and at the chair of Security and Telecommunications. In his previous life, he also was within the top 10 of the bug crowd research and pen testing community. He enjoys playing and organizing Capture the Flags, and just this year he won the Applied Research Conference of the CSAW conference. So, yeah, winner of the conference awards. The talk is called "What's a Fuzz? Finding O-Days in Web Applications with Coverage-Guided Fuzzing." Sebastian will talk about a framework for coverage-guided fuzzing for PHP web applications and introduce that framework and explain the challenges he faced when bringing coverage-guided fuzzing to PHP web apps. Please welcome Sebastian with a huge round of applause.
Wow, thank you very much for the very warm welcome. I didn't expect the room to be that full because there are two other really great presentations going on in the other rooms. So thank you for being here. And also a big thank you to my co-authors of this publication, Lorenz and Professor Seifert, because without them, this work would not have been possible. So I usually give my presentation as a sort of story, so I'll be your storyteller for the next 60 minutes. But I was already quite well introduced, so I skip the part on the left side and just continue with the right side. So my first congress was roughly 10 years ago. It was a 31C3. And yeah, back then I didn't really expect to be at the stage in front giving a presentation at some point, but now here I am. So to all the first-timers or more regular C3 attendants, yeah, if you do some interesting stuff, and I'm sure you do, then hand it in for the CFP and take my place at a future event. So the story will be about Fuzz. Fuzz is a fuzzing framework, and we go through different phases of developing Fuzz and using Fuzz. So we'll start with a short introduction and the motivation that we had to build this tool. Then I give a brief introduction to fuzzing. Then we'll go on with what Fuzz actually is and how it works. Then I'll talk about the findings, including the 0 days that we were able to find. And then there's a bit of what's left to be done, where you could contribute to this work, to this framework. And in the end, we'll have time for some Q&A. So let's start with the introduction and the motivation. So what was the motivation for this work? As already told, I used to do a lot of bug bounties back then during my studies, and it was a quite nice way to earn some money as a student. So still, I think it's a good side job, so why not try to find some more vulnerabilities on the internet, especially cross-site scripting, SQL injections, remote command execution, and some others, then report them either to the website operators directly or through some responsible disclosure or bug bounty program to improve the web security and maybe gain some CVEs or CV enhancers, like some people call them, and also some bug bounties. But as a PhD researcher, I don't have much time, right? I have to do research, I have to do teaching. Teaching takes a lot of time away from my life, but it's fun, it's nice. So yeah, there's no time for manual testing and source code reviews of some applications. Although it is fun, I used to do that. So why not find some automated way to discover these vulnerabilities and then report them? So this is something that is called fuzzing or fuzz testing. And in the end, my third motivation was to somehow use it as part of my research career for an academic publication. So I looked into the existing research and noticed that there's little research and little publications on web application fuzzing. So I thought, well, it's quite established in the binary application domain. Maybe we can apply some of these concepts to web applications, and then this might have enough novelty for a publication. So with that said, let's move on to the background. Who does not know what fuzzing is? Who has not heard of fuzzing? Please raise your hand. Okay, quite a few people. Apparently most of you know what it is, which is great, because you might not know how it can be applied or how different methods can be applied to web applications. So for all the people that were not yet familiar with the term, it was apparently coined almost 40 years ago by a professor at the University of Wisconsin, and it was described as a simple technique for feeding random input to applications. So what does the simplest form of fuzzing look like? We have a fuzzing program on the left side, and we have an application that we want to fuzz on the right side. So the fuzzer generates some random input and sends it to the application. The application then processes this input, and then there are two possible outcomes. The first one is that the application properly handles the input and nothing special happens, so it's okay with the input. And the other case is that the application fails to properly handle the input. It might crash, it might show some weird behavior. So this is where the fuzzer notices, okay, the application misbehaved, and this might be a potential vulnerability or something about this particular randomly generated input caused the application to misbehave. And why is this called black box fuzzing? The reason for that is that the fuzzer does not have much knowledge or information about the fuzzed application and how it processes the input. So it's like a black box. So some research later, people came up with the idea of actually improving the fuzzing process by adding some coverage guidance or feedback mechanism into the application. So you can see the different functions. Let's see if the laser pointer works. Not that good. So the functions that you see on the right side in the application are instrumented, so that the fuzzer in the end knows what code was executed for this particular input. And this feedback, also called coverage, is then fed back to the fuzzer, and the fuzzer can process this feedback in order to optimize the random input for the next iteration, or in order to get more information about a potential bug. And usually these fuzzers optimize for the highest coverage, because the goal is to fuzz as much of the application's functionality as possible. So if you type fuzz testing or fuzzing into Google Scholar to look for some academic publications, or if you would type it just into the regular Google, you would find quite a lot of results, more than 68,000 in this case. So there's lots of projects and a lot of research activity going on in the domain of fuzzing, which is great. So for example, I've brought you a few projects. American Fuzzy Lob was developed by Elkamtov and then extended by the fuzzing community into AFL++ with additional features and some improvements. And then back in 2016, Google started the OSS Fuzz project, which was just after the Heartbleed bug was discovered in OpenSSL, in order to fuzz different open source projects. And since then, it has found more than 10,000 vulnerabilities and over 36,000 bugs in more than 1,000 projects, according to their website. And then, of course, there are many other projects. I couldn't list them all, but with regards to this year's topic, there are even fuzzers that try to fuzz x86 processors to find some illegal instructions, maybe. Yeah, so there's a lot of fuzzing in different domains going on. But with what you've seen, there's quite a strong focus on binary applications and usually the resulting memory corruption vulnerabilities. So most of the fuzzing research, as far as I know, focuses on applications written in C, C++, or some other binary level language, and they usually try to find memory corruption vulnerabilities like stack overflows, buffer overflows, heap overflows, and so on. So this is where I was wondering, wait, what about web applications and web vulnerabilities? I do my research in the web security domain, so I would like to find these web vulnerabilities. Why not using Fuzz testing? But why is there not so much research on that? And one reason for that could be that in contrast to the binary application fuzzing, where you had the fuzzer and then the application that you wanted to fuzz in direct contact, with web application fuzzing, you have a web server in between those two programs. So a traditional or a fuzzer would have to create correct HTTP request, which goes through the web server, so that the fuzz input then reaches the web application. And there are traditional web application fuzzing tools. Fuzzing exists for web applications, but according to OWASP, fuzz testing or fuzzing is a black box software testing technique which basically consists in finding implementation bugs using malformed, semi-malformed data injection in an automated fashion. Again, the keyword is black box fuzzing. So this limits the fuzzer's possibilities to get feedback from the web application. Why? Because the web application might run on a different system than the fuzzer, and depending on how the testing is done or how the application behaves, it might just return an empty website or just a generic HTTP error if something breaks within the application. So there's limited feedback for the fuzzer about the triggered vulnerabilities, and the fuzzer has to find ways to use a set of predefined payloads or heuristics to send to the application because it has no idea what the potential vulnerabilities could be on the web server side in the application. So traditional fuzzing using the black box approach is a bit limited. So my question that I asked myself was, can we apply coverage-guided fuzzing to web applications? So can we instrument the web application and improve the fuzzing process and maybe find more bugs using that approach? But it turns out there are several challenges. What are the different challenges? There are 4 of them, so let's go through them. So the first challenge is finding out what to fuzz. With the binary application approach, you have usually one specific input path. You either write the random input to standard in, or you write it to a file which is then read by the application, but usually there's just one specific way to get the input in. But with web applications, we might have different endpoints and different inputs. For example, if you just think of a normal web application, you might have a register endpoint which takes email, name, and password parameters. You might have a login endpoint which takes a different set of parameters and some other websites, and even static resources that you don't want to fuzz because there shouldn't be any processing happening on the server. So how do we know what to fuzz? Once we know what to fuzz, the next question would be, how do we mutate the input? How do we randomly generate input to give to the application? And again, web applications are a bit specific about it because they require these specific parameters to function properly. If you omit the email parameter in the registration endpoint, the registration will just fail, and you wouldn't test the actual registration application logic. So you have to provide the correct parameter names, but then just change the different values. And then the next question is, how do we trigger the vulnerabilities? As you can see, for cross-site scripting issues, you might have to inject a specific string to trigger that vulnerability or to detect the cross-site scripting issue. Same goes for SQL injections. You might have to inject special characters in order to detect this vulnerability. So with a black box approach and just randomly flipping bits in the input, it would take quite a while until we end up with these specific strings. So how can we overcome this challenge, and how can we trigger vulnerabilities in the application? The next challenge is the instrumentation and coverage collection. So as I said earlier, coverage-guided fuzzing depends on the instrumentation of the application and the feedback, the coverage which is then passed to the fuzzer in order to work properly. So how do we do that? As I said, these two parts, the fuzzer and the application, might run on different systems or in different processes. So how can we achieve that and solve the challenge? And then the next part is the vulnerability detection. Once we have instrumented the application and we get back the HTTP response from the application to the fuzzer and even some feedback, how do we then detect the vulnerabilities? There might be different methods. We might be able to detect cross-site scripting from the HTTP response, but how do we detect SQL injection, remote code, or command execution? Because that happens on the web application. So we somehow have to get more information about these potential vulnerabilities to the fuzzer so it can detect them. We were not the first to actually work on these challenges and try to solve them. There was quite a bit on related work, or to emphasize, quite little bit of research. I started to do this research in the end of 2022, and there were only WebFuzz and CFuzz which actually tried to do coverage-guided fuzzing on PHP web applications. And then concurrent to our research, The Witcher was published and Atropos was published this year, 2 months after our publication. So what you can see in this table is that the approaches usually focus on single vulnerabilities. WebFuzz had only cross-site scripting, CFuzz command injection. The Witcher had 2 vulnerability classes, and Atropos implemented several ones, which is quite nice, but they focused on web server-side vulnerabilities, not client-side ones like cross-site scripting, open redirection, or some other classes. And then all the approaches by the related work, they require changes to the fast application source code in order to instrument the application, or they had to modify the PHP interpreter with low-level changes or even external commands. So I had a few ideas for improvements. For example, about the instrumentation, can we do that without actual code changes? So can we just create a system, a framework where someone can place their web application inside a Docker container and then get started fuzzing that application for web vulnerabilities without having to recompile a PHP interpreter or modify the application source code, which might break it in some way. And the other motivation was to actually create a framework that would support multiple common vulnerability classes. So we won't have like tens of different fuzzers in the future, but maybe one framework which could be extended for different vulnerability classes. And I also came up with one alternative endpoint collection method. All the approaches used a crawler-based approach, and I thought maybe I can find a different one. So let's talk about Fuzz. Fuzz is the framework that we have developed. You can see a figure of that on the slide. It is modular, it's Dockerized, and it's open source. You will get the link to that project on the last slide, just to keep your focus on the slides, not on the code. So yeah, every box that you can see in this schema is more or less a separate Docker container. So everything is Dockerized, the browser, the crawler, the generation containers are Dockerized, the fuzzer is Dockerized, and the web server and instrumentation is Dockerized as well. So as I just said, in addition to the crawler-based endpoint detection approach, we implemented a browser-based approach. So that's why there is a box with a browser next to it. And then we have in the middle the core component, the fuzzer. And you can see that there's fuzzer 1 to n. So actually our fuzzer supports parallel fuzzing from the get-go. So you can just start several instances of that fuzzed for parallel fuzzing, which might improve the fuzzing speed or the results in a positive way. And the fuzzer supports 7 different vulnerability classes. So from SQL injection over remote command execution, external entity injection, path reversal, insecure deserialization, open redirection, and cross-site scripting. And on the right side of this figure, you can see the instrumentation, which we managed to implement in a transparent way. So you have this container where the PHP interpreter is instrumented in one specific way, and you as a user can just place your web application inside that PHP container and then have it instrumented in a transparent way so that it doesn't really notice that it's being instrumented and being fuzzed. So we don't have to do all the changes. And then we have one red box in the right-hand corner that is necessary for the vulnerability detection. I'll get to that in a few slides. So we do some exception and error handling and function hooking to get more information about what the application does and where the potential vulnerabilities might be. So let's go through the different challenges, and I'll explain to you how Fuzz solved them. So as I mentioned, the crawler-based approach used by related work comes with long runtimes, at least in the few examples and readmes that I saw. And I believe a crawler-based approach might not be the optimal way to find the endpoints that we want to fuzz, because the crawler might get stuck, it might not have the capabilities to use some interactive websites functionality, or it might fail to fully explore the application by getting stuck and not finding some endpoints in some hidden JavaScript files or whatever. So let's try to do something different that also allows to do more directed fuzzing. So we came up with this browser-based approach, which is manual, but it's only manual in the very first step in the beginning. So once you set up the web application in the instrumented PHP web server container, you explore the web application using your browser and your developer console open. And if you tick the right box, it will preserve all the requests that were sent to the web application from your browser. So the next step is then to export these requests into a HAR file, which is essentially just a large JSON file with all the information about the request and the responses that your browser received or generated. So, for example, you would see in the code that there's a SQL lie endpoint with a parameter ID and submit equals submit and then some user token. So this HAR file is then processed by our Fuzz framework, by the different components on the left side, to actually extract the different endpoints that you'd like to fuzz and to generate suitable configuration files for the fuzzer. So the configuration files are just JSON files again, and they define, okay, we will have the target endpoint vulnerability /SQLi. Then we'll have to set a cookie with the name security and the value low, because that's how the DVWA works. It wants to have that specific cookie. We also define the login session cookie to be PHP sys ID, so it wouldn't be mutated or changed by the fuzzer. Otherwise, we would get locked out of the application. And then the interesting part is here below with the query parameters in line 11, where we define the two parameters that we saw earlier, ID with the seed of Fuzz, and the submit value, or the submit parameter with the value submit. And then in line 16, you can see that we set the submit parameter to fixed, so this parameter will not be fuzzed. So the configuration allows a quite good customization of what should be fuzzed and how the application should be fuzzed. So how do we fuzz the web application now? How do we solve the second challenge of the input mutation? If you remember the figure with the fuzzer, the web server in the middle, and the application on the right, you might have remembered that there was the HTTP request. We talk HTTP between the fuzzer and the web server because that is how the web works. And then the web server parses out the different parameters and passes them on to the PHP application. So we have to generate a valid HTTP request in order to get our parameters and values to the application. We can't just randomly change bits or bytes on the whole HTTP request, because the web server would then reject the HTTP request. It would say, yeah, this request is malformed, it doesn't comply to the HTTP standard, so I'm not going to pass any values onto the PHP application. I just reject the request, and then we would have done one fuzzing iteration, which was ineffective because the input did not reach the application. So since Fuzz is written in Python, we just use the Python request library to pass it all the different values that we have. For example, the URL to the endpoint, the different parameters, the cookies, the headers, and then it will generate a valid HTTP request for us, which is quite nice. And we know that the parameters will actually reach the application. Then, as mentioned in the second or the first challenge with the endpoints, we have to keep the different parameters and endpoints mapped together. So if we would send a different set of parameters, for example, to the register endpoint, and this set would not have the email, password, or name parameters, this endpoint would say, okay, you're not providing the right set of parameters. I'm not going to process this input. I just reject it, and then we have nothing won. So we said, let's keep these parameter names the same and just mutate the values so we can actually try to fuzz the different application logic behind the different endpoints. So these are a few lines from the parameter selection and then mutation of a specific value. And in this case, we will change the value, the seed value fuzz of the parameter ID. So how do we change these values? Well, we do it with the byte-wise changes. In theory, we could also have done bit-wise changes, random bit flips, or other approaches that are used by the binary application fuzzers. But since the web applications usually work with printable ASCII characters, except for maybe file uploads, we thought, let's keep it with random bytes. So we add, replace, modify single characters, and also at random chance, we insert some vulnerability triggers, like for cross-site scripting, for path reversal, or for some of the vulnerability classes that need specific structured input to get triggered. And here again, a few lines from the fuzzer itself. As you can see, you can see the modularity. We have this default mutator class. We have some subclasses with the different changes to the input. And if you would like to improve upon this input mutation, you could just add your own mutation classes or change the default mutator. So in our example, we would change the parameter fuzz and maybe add a single quote character, which might be even enough to discover some SQL injections. So let's talk about the instrumentation challenge and the coverage collection. The reason why we can do that without changing any of the PHP interpreter source code or the Fuzz application source code is because we use 3 different open source extensions. We use UOps for interception and hooking of different native and non-native functions. And then we use 2 different plugins that provide a way to collect coverage of the executed PHP application. And again, this also makes our approach agnostic to PHP versions. Some of the related work only works with PHP 7. Nowadays we have PHP 8. But we are confident that these open source plugins might be maintained by the community in the future, so our instrumentation approach might work across newer PHP versions. So how does the function hooking work, which is quite a crucial part of our instrumentation approach? So UOps provides the UOps set return function, and you can pass it the name of a specific function you would like to hook into and overwrite the return value. And we use that approach to hook into some of the native PHP functions and some of the non-native PHP functions provided by the web application that we are fuzzing in order to wrap those function calls in a try-catch. And why do we do that? Well, on one side, it allows us to modify the return values, for example, for authentication authorization functions. So using the function hooking approach, we can simply make is logged in, is admin, check CSRF nonce, or any other security-related function return true or whatever positive value it should return, so that the fuzzer actually finds more vulnerabilities in the code and does not get stuck at one of these functions. Then we can also catch suppressed exceptions errors. from over 60 risky functions that we instrument in our instrumentation. So you might have seen in PHP code this @ sign in front of a function call, which suppresses the exceptions and errors generated by that function. And by wrapping that MySQL query in our hooking approach, we can actually see the exception, which would have been generated and then emitted by the code. So we would see you've got an error in your SQL in syntax error message, although the application does not see it or wouldn't show it to the user. So we can better detect vulnerabilities with that. And then we also use the function approach to hook into the set exception handler and set error handler functions to define our own exception error handlers in order to get coverage even when the application exits due to an error or to an unhandled exception. And this is quite nice. So how do we get the coverage so the fuzzer knows how to optimize the different inputs? For that, we use the PHP configurations auto-prepend file and auto-append file to initialize and stop the coverage collection. And again, we have both xdebug and pcoff that couldn't be used, so you can decide when deploying the PHP container which of the both instrumentation approaches to use. Pcoff is claimed to be a bit more performant and faster than xdebug, but we decided to just cover both of them. And they will start the collection of the different executed functions and then in the end also stop collecting them, writing the resulting JSON file to the shared volume to make it accessible to the fuzzer. All right, how do we detect vulnerabilities? The final challenge. Well, once the fuzzer receives the response to the HTTP request and the coverage report, it can use both information sources for vulnerability detection. For that, again, we implement different classes, and for cross-site scripting and open redirection, we can use the HTTP response. And for the other vulnerability classes, we use the exceptions and error hooked by UOps. So let's talk about the findings. I think many of you are here for vulnerabilities and 0 days, right? Who is? Raise your hand. Oh, damn. Okay. I hope not to disappoint you. So when you develop such a framework, you would want to have a specific baseline test for it. So our first question was, how well does Fuzz perform in comparison to other vulnerability scanners? Does the coverage-guided fuzzing approach even work? Does it bring any benefits? So in our first experiment, we fuzzed for known vulnerabilities. So we set up the different intentionally vulnerable web applications. You might have heard of some of them, for example, the damn vulnerable web application. And there are some more used by related work, so we used them as well. And we also chose some publicly known vulnerabilities in some specific WordPress plugins. And for the scanners, as the contesters to our approach, we chose Burpsuite Pro, the Z-Attack proxy, Wapiti, and WFuzz. So to make it short, Fuzz managed to discover more vulnerabilities that it's able to discover than its contesters, and the coverage-guided approach gets pretty much visible in the server-side vulnerabilities. So if you look into the second row of the totals, you can see that we find up to 98% of the server-side vulnerabilities, where the other black box scanners only find up to 58%. So the coverage collection and the function hooking actually gives us a benefit, gives us an edge over the other tools, which is nice. So now Thank you, I didn't expect that because that was quite boring, wasn't it? So can we actually use Fuzz to find new vulnerabilities? So we thought, okay, how do we get a lot of potential source code written in PHP that is publicly available that we can fuzz? So we found WordPress plugins to be a suitable target, and to make it a bit harder for our fuzzer, we decided to not fuzz plugins that have like 100 installs or something, but ones that have over 300,000 active installs. So we downloaded 183 of these popular public plugins, and yeah, they all had over 180 million active installations at the time of writing. Since we can't do the manual browser-based approach for all of them, we decided to use a programmatic approach and extract the different API endpoints defined by WP Ajax. And in the end, we came up with 1,090 API endpoints with 1,085 parameters and 115 plugins that we fuzzed. But in order to actually fuzz authenticated and unauthenticated plugins, we had to disable some security features using the function hooking approach that we just explained. So we disabled authentication, authorization checks, some security checks, and then we fuzzed these API endpoints with Fuzz and Burp Suite Pro. All right. So can we actually find vulnerabilities with Fuzz? Yes, we can. So these are the results that we got. And you can see that at least for path reversal issues, Fuzz found a lot more valid findings than Burp Suite Pro, although Burp Suite Pro found more cross-site scripting vulnerabilities than our approach, which is partially due to the limitations of the web fuzz algorithm that we used. So we notified all the affected plugin authors, and they are quite quick to respond to our emails and also to update their code, which is awesome in my opinion. Yes. So there was only one issue. We notified the plugin authors, but it turns out that some of the issues were just programming bugs. I mean, we didn't report the programming bugs, but some of the issues were also interesting findings because we discovered some bugs, for example, malformed or invalid SQL queries or file accesses to non-existent files. So you could actually use Fuzz to identify programming mistakes in your plugins, which is also quite nice, but not the point of Fuzz. So the other things that we discovered were hard to exploit issues. Fuzz correctly discovered the identified vulnerable code path, so it managed to generate an input that ended up at some function that could be vulnerable to one of the defined vulnerability classes, but these issues weren't really exploitable. And why? Because remember, we disabled some security checks in the beginning to fuzz these authenticated API endpoints, and it turns out all of the issues that we found, which are in theory valid, are only exploitable by authenticated administrators. So now the issue of the threat model arises. So if an administrator can edit PHP code through the theme editor in WordPress, they have remote code execution by design. So there's no point in using a vulnerability in one plugin that allows some administrator, to read some file, right? So how do we still find vulnerabilities? So we had to take a step back. We waited a second, and then decided to dig a bit deeper. So maybe there's some weird WordPress behavior that we can abuse, or maybe some other issues that could lead us to have actually valid vulnerabilities. So one thing that we noticed is the isAdmin function. And my first interpretation of the isAdmin function was that it actually checks whether the user is an administrator or not. But if you actually go into the documentation of WordPress.org, it says that the isAdmin function determines whether the current request is for an administrative interface page. It does not check if the user is an administrator. And I was, wait, what? I was confused, and I thought if I'm confused, then maybe some developers are confused as well. So even scrolling down the page, we notice that isAdmin only checks whether the requested page is within the /wp-admin page. And also one comment says that isAdmin returns true for Ajax request that we were fuzzing with our approach. So, well, maybe actually there's still a way to make this a vulnerability, but still we have to be an administrator, which isn't great. So I looked at the WP-Scan CNA that handles WordPress-related security submissions, And they say on the submission form, you have to be an administrator, or if you're an administrator, you can only report vulnerabilities if they are in a multi-site environment. So I looked up WordPress multi-site installations, and I noticed, well, there are actually two different kinds of administrators. Great. One administrator type is the network administrator, which administrates the whole WordPress installation and has all the code execution privileges. And then there are site admins that control the subsites and have limited rights. So now the threat model changes. If we are a sub-site administrator and we can use a vulnerable plugin to actually attack the whole WordPress installation, we might have a proper vulnerability. So, yes, we looked through the different vulnerabilities, the issues that we discovered, and actually found two different vulnerabilities that qualify as a valid issue. So reported them, got a CVE assigned, and one of the vulnerable plugins was a pop-up builder in which we found a server-side request forgery and arbitrary file read. So now, if you remember correctly and listen carefully, I said we Fuzz plugins with 300,000 installs, right? And now currently this plugin has only 200,000 installs. So why is there a difference? Well, I think the popularity might have tanked after our security report. I hope not. But still, it is at where it is now. So how does the vulnerability or the exploit look like? I shortened it quite a bit, but if you want to read the whole write-up, you can go on the zeroday.work blog post where I posted a write-up on the issues. In essence, you can send a post request with action sgbpv import subscriber, and then the import list parameter is vulnerable to path traversal or server-side request forgery in the admin Ajax endpoint, and if you send this payload, you will have, or you will be able to read parts of the file. So this is the first issue that was then in the end valid. So let's move on to the next issue, which was also a local file inclusion vulnerability. Again, the plugin had, or currently has 500,000 installations, but back then it had, if I remember correctly, 600,000. So again, 100,000 down since our report. Yeah, I hope people don't blame us on that. So what was the issue in that plugin? Again, we can send a post request with the widget parameter being vulnerable to local file inclusion, but this exploit had a little twist to it because it will only be able to include a widget or a file with a PHP suffix only if there's a directory with the same name without the PHP suffix in the same folder. So for demonstration purposes, we used /temp, created a file, and as you can see, it's being included with foo hacked in the response. But actually, there might be something exploitable, or maybe something exploitable, because there's a network directory with a network.php in multi-site installations. All right. So these are the two vulnerabilities that we found. And now let's go to the outro chapter. What can you do with Fuzz? How can you find your own vulnerabilities? And how can you help to extend the Fuzz framework? There are some challenges that I was not able to solve yet. I hope that there are some brilliant people in this room that could help with this, because, for example, the UOps extension that we use for function hooking is only able to hook into PHP functions, but not PHP expressions. And PHP expressions are a different language construct that, for example, eval or include or require belong to. So we cannot detect local file inclusion issues right now. Also, there's limited support for stateful and multi-step actions. So if a vulnerability requires to send a request there, and after that there, so sequential actions, Fuzz cannot detect these issues right now. But what we can do is parallel fuzzing of different endpoints. So if the input goes in here and it's being exploited on this other input, then Fuzz can detect this. And again, fuzzing speed is also different in comparison to binary applications. By binary applications, Fuzz with up to tens or hundreds of thousands of executions per second. With Fuzz, it highly depends on the web application. So for DVWA, which is quite slim and fast. We can get several hundreds of executions per second, but with WordPress, for example, it's in the low tens or hundreds. So it's not that fast in comparison to a binary application fuzzing, so there's a lot of room for improvement. And then future work, obviously. There are some other vulnerability classes that could be implemented in the Fuzz framework, for example, server-side request forgery, header injection, code execution, and some others. And since our fuzzer only implements some basic fuzzing algorithms, it would be interesting to see if we can actually implement or adopt some of the AFL++, libAFL, more sophisticated fuzzing algorithms, or if we can even integrate some of the instrumentation parts into the AFL++ framework. And then there's just the last point: we need to fuzz more, we need to find more vulnerabilities, so please feel free to fork and contribute to the Fuzz project. It would be great to see some improvements to that. It's by no means perfect, but it should be usable as it is right now for the basic vulnerability discoveries. So in conclusion, what I have presented to you is our Fuzz framework, which is modular and supports PHP web applications with up to 7 different vulnerability classes. It's open source. It has outperformed the other vulnerability scanners in our experiments. So I believe it's some good approach to actually find vulnerabilities. And it also shows that the coverage-guided fuzzing approach is applicable and a promising approach to uncover such vulnerabilities. But still, there's room for optimizations and further research. So since, again, I believe we are quite a lot of computer nerdy people in here that like to code and like to find security issues, it would be nice if you could contribute. And then the most important thing is to still have fun at 38C3 and keep on hacking, maybe on this project, maybe on other projects. But if you find vulnerabilities, please be responsible. Don't post them in the wiki on the hacked page. Report your bugs. Do the good thing. Be the white hat hacker. I would be thankful for that. So with that, we reached the end, and they lived fast happily ever after. So I believe now we have some time for questions and answers. And while you line up for the microphones, you can find the full publication behind the QR code, or if you Google for what all the Fuzz is about, you will find it as well. It's open access, so you can just download the paper, read it, and you can also find the code on GitHub. The slides as well, and if there are still any questions or you'd like to collaborate or work on Fuzz, you can send me an email. Thank you.
Thank you, Sebastian, for the awesome talk. If you have questions, please line up at the microphones in the room. There are 6 of them. Seems we do not have a question from the internet. Checking here. Also, if you're leaving the room, please do that quietly. Yeah, down here.
Hello, thank you for the awesome talk. Let's say I wanted to do this with Node.js applications instead. So the coverage part and I guess the hooking part would be what needs to be replaced. Other than that, it's not PHP specific, or did I understand that not correctly?
Right now, Fuzz focuses on PHP applications, so we have only tested this with PHPs, and also the instrumentation is specific to PHP. But if you manage to swap out, as you said, the instrumentation part, so you can generate coverage, which is then passed to the fuzzer as the JSON file in a format that's also similar to what pcov or xdebug generates, or the exceptions that you capture, then you can totally use the Fuzz framework.
Okay, thank you.
Thank you. Over here, your question.
Thank you very much for the talk. I was wondering if you had considered bypassing the web server and directly executing PHP without the actual HTTP overhead, and if what were your reasons for the choice you made to go through the full stack rather than just talk to PHP?
I have no idea where the microphone was, where the question came from. Oh yeah, perfect. Hi. Yeah, you're totally right. This is something I wanted to work on as a next step, but it turns out that this is exactly what the publication Atropos did. They called the fast CGI PHP server directly with the parameters, which is one thing that you could do. The reason why we focused on the challenge with the web server was that we thought, okay, maybe sometimes web applications come with special configuration, like with the Apache web server, you have these htaccess files with specific directories and then should be passed by the web server because it might rewrite the URLs or do some other fancy stuff. So we thought maybe that's a good idea, but again, you're totally right. This is also something that would likely speed up the fuzzing process.
Thank you. On the right side?
Hi, thanks for the talk. So you mentioned the mutators being random for in some cases. Is there a way for them to be deterministic, or is it purely real randomness?
Right now we have implemented it with real randomness, and yeah, I would leave the answer to maybe more experts on the fuzzing domain. I think you can do it deterministically. But yeah, this is something you could do. You could just implement your own mutation classes and then load them into Fuzz and yeah, see if it makes any difference.
Okay, thanks.
Thank you. Yeah, on right. Go ahead.
One question, great talk. You only found single-stage vulnerabilities, no multi-stage, or also multi-stage vulnerabilities?
That's a bit tricky. As I said, we do not really support sequential multi-stage vulnerabilities because that is something that Fuzz does not support. But we support, we support vulnerabilities that do not require a connection between two requests, right? So in the damn vulnerable web application, there's one SQL injection, the high level, where you have to give the input through one endpoint, and then the vulnerability is triggered on the other endpoint. And we can find this vulnerability by fuzzing those two endpoints in parallel, because the one fuzzing instance will generate an input that will end up somewhere with a payload, and then the other instance will trigger the vulnerability and detect the vulnerability through the function hooking.
Okay.
So it's yes and no.
So I guess this is why you haven't tried Juice Shop, because there's a lot of multi-stage or logic.
As far as I know, Juice Shop is implemented in Node.js, isn't it?
Okay. That's true. Okay, you're right. Thanks.
All right. The microphone in the back, your question.
All right, I'll keep it short. So the endpoint discovery, as I understood, that was like manual browser interaction, right? Have you explored using end-to-end frameworks like Cypress for that might already exist in some projects?
Good idea. We have not looked into that, but yeah, happy to do so.
Okay, thanks.
All right. Microphone on the right-hand side, your question.
Thank you for your talk. I want to know, can you fuzz also a closed PHP source where you can't look in the source code?
You can fuzz that, but then you're back at the black box approach, where you just throw things at the black box and hope that something sticks. But with our coverage guidance, you have to do the instrumentation, so you have to have the source code.
Thank you.
And again, the microphone on the back.
Yeah, thank you for the talk. I think the framework is very interesting and an interesting approach for, pen testing web applications. I was wondering if the comparison to other scanners like Burpsuit and so on isn't a bit unfair because they only can rely on like black box testing while your approach kind of has code access. So what's your opinion on that?
You are right. We took these tools because they are the state-of-the-art open source and commercial tools, so we wanted to see how that compares. But actually, I brought one extra slide. We wanted to also compare to the related work, which actually uses coverage-guided fuzzing with our approach. But it turns out that due to the instrumentation and how it's done by the other approaches, we weren't able to get some of these tools to run. I believe Fuzz was not published, or it has its code not published, so we cannot really use that. We didn't get Witcher to work, unfortunately, for the comparison, and Atropos was not yet published, so we also did not have the code. But we looked at these publications and compared the number of vulnerabilities that they reported for their tools, and as you can see, Fuzz still finds more vulnerabilities in these intentional vulnerable web applications. Yeah.
Thank you.
The microphone on the left.
Not sure if I got it right. When you discover the things that you mutate, you're just mutating the parameters. You're not throwing random different query string parts at the application.
It was a bit hard to understand, but I think your question was if you're just randomly mutating characters or if you're also using some specific payloads, right?
It was about the discovery. You reported that you're just mutating the parameters you discovered from the manual exploration.
Yes.
And then you're mutating the values given to the query string parameters. Is that correct? Or do you also mutate the query string itself randomly?
No, we split up the parameters. So we have all the key and values separately. We do not mutate the whole URL, we just mutate the parameters. So actually, we keep the parameter names the same, we do not change them.
Okay.
It would be interesting to see if we can mutate them as well, but I believe it would 95% maybe lead to invalid requests and there wouldn't be much gain.
Well, it's not so much about mutating the key names, but choosing arbitrary keys of the whole set. So you might be missing relevant vulnerabilities that stem from unintended interpretation of keys that are not standard, but probably in the application. Not sure if I probably will take this outside.
Yeah, actually quite a good idea. I think this is something we thought about, but then decided against it. But I think you should be able to implement this with our framework if you change the mutation classes. So we just randomize the key names. That should be doable.
Thank you. The gentleman over here.
Thank you for the talk. It looks like you wrote oracles for a lot of different web vulnerability classes, which seems like one of the difficult things to do to make fuzzing really effective for web fuzzing. I'm wondering if any of these can be repurposed into dynamic defenses. So instead of fuzzing, you actually use them to protect against attacks that are happening in real time.
I don't really know how to answer your question.
I guess how do you detect the vulnerability classes that you detect?
How did we detect the vulnerabilities? With the function hooking. So as I explained, we hook into, for example, the MySQLi query function, and then if fuzz input reaches that function and causes a exception because it will return you've got a SQL broken SQL syntax in your SQL query, then we use that information in the exception message in the fuzzer to take this as an indicator for a SQL injection vulnerability.
Okay, thank you.
Yep.
On the left, next to the camera. Oh, sorry, you were just waiting. All right. Dan in the back.
I was wondering, does this approach also work for obfuscated PHP code?
Good question. I think it depends on the obfuscation, right? Like, at some point, or I'm not sure if you can actually obfuscate native PHP functions. I'm not sure about that, because at some point, these should be called. If you have, like, the function file that opens a file, at some point, obfuscated code should be calling that function. So we instrument that function, and we should be able to detect the vulnerability in that. But we wouldn't be able to hook any non-native function that the application provides, unless we know the obfuscated function name.
Thank you.
Thanks a lot, Sebastian Neff, for answering all the questions and for the great talk.
Thank you.